Hey everyone, this is a lesson on dot product 6.2, and this dot product, there are some cool applications to it, like with work and force kind of problems, especially to do with physics, but we are not going to get to those, so please hold off even though your notes show them, okay? We're going to get to a few things about dot products, how to, and also talk about orthogonal vectors, all right? Let's get started. Definition of dot product, part 1. Let U be W be vectors in the planar space and let C be a scalar. Remember, C is a scalar, which means it's a constant, okay? All right, so if you have two vectors, the dot product of them, of course, U1 and U2 are the horizontal and vertical components of this vector, say along with V1 and V2. U times V, the dot product of U and V, that's why it's called the dot product, is the sum of the horizontal components, the product of, and the product of the vertical components, all right? Also, dot products follow the properties of anything that you know of, okay, like in algebra. U times V is V times U, commutative property, associative property, or distributive property, associative property. Also, this is the magnitude of U when you square it. It's the same thing as U times U. 0 times U, it becomes 0. You know, it follows the same kind of structure as when your classic algebraic properties, okay? All right, let's get started with some examples, okay? Find the dot product. That's an easy one. If you don't like the linear combination notations, you are more than welcome to always write them into component forms, okay? Component forms translated goes like that. And let's actually write, U1, V1, U2, V2. And let's perform the dot product. Easy peasy, okay? Remember, it's the sum of the horizontal components and the vertical components. All right. Oh, sorry, negative 9. Oh, sorry, negative 3. And, negative 2. All right. Let's multiply them together. It's going to become negative 4 times negative 3 plus negative 3 times negative 2. Okay? So for some of you, it may be hard to wrap your head around this kind of calculation, right? But you'll get used to it. 18, and that's going to be 30. Now, what does this dot product mean is the physics aspect of it, and unfortunately, we're not going to talk about that, but for the calculation, this is what you do, all right? Now, use the dot product to find the magnitude of U. Well, the magnitude of U is what? Isn't it just these components squared? So wouldn't you agree that the dot product to find U is actually just simply U times U, and that's why it's the dot product, really, right? And the dot product is that this guy is your U1, and this guy's also our V1. It's U2 and V2. It plays both roles, right? So it's going to become negative 8 times negative 8, the sum of 15 times 15, right? So we get 64 plus 225, which gives us 289 root of, and you get 17. Okay, the dot product and the magnitude is really similar if you're only talking about the vector itself, okay? All right, now let's switch gears and find the angle between the vectors, all right? Now, the angle between vectors has, of course, a formula that you must remember, but the formula is not very hard. Also, there's a beautiful formula, there's a beautiful proof of it on page 460. If you want to take a look at it, you can, okay? It tells you how to calculate and why this is true, like this formula here. Why it's true. And you have two vectors, U and V, right? The angle between, why it's this. What is this? Cosine of theta is equal to dot product of U and V and the magnitude of U and V divided by. Okay, let's do that again. All right, so how do you find the angle between two vectors? You simply take the product of your vectors. Okay, you take the product of your vectors, and then you divide it by the scalar, right? Which is the magnitude of the vector's product of, right? Another variation of this guy would be, you take the dot products, and it's equal to the magnitudes times the cosine of that angle. But if you're looking for the angle, of course, you have to take the inverse cosine of that. Okay, again, there's a beautiful proof using law of cosines. Go take a look on page 460 now. Stop the video. Okay, the video ain't going anywhere. All right. All right, how was the proof? I hope it was beautiful, okay? Yeah, it's very easy to understand, and you know law of cosines really well, so it should have been pretty simple for you. All right, next, let's try finding some angles between. So we have vector u and vector v. Again, this is number 16 from your homework, okay? All right, and if you were to picture this, it's 5 and 2, so like maybe u is here, and your v is 6, -1, so maybe like here, okay? V. So we're trying to look for the angle between here. Let's go like a little thinner, like here, right? Whoa, that was bad. Okay, let's go back, okay? Sorry about that. Okay, so we're looking for the angle between these two vectors, so like this. We know definitely it's greater than 90, but I think I may have exaggerated the point a little bit, so let's make it a little bit, so it's a little bit more angled, okay? So we're looking for that angle. We definitely know whatever we solve for that angle, we must get over 90, so let's check, okay? All right, so again, whenever I learn a new formula, I'm going to keep writing it. So I'm going to do, it's the dot product of my vectors divided by the, magnitude of my vectors multiplied together, okay? All right, my vector is 5, 2 times -6, -1, and my magnitude, and here is another thing, you guys, I guess I'll just write it for now, but you don't have to write these kind of things for me anymore, times -6, -1, okay? And also, you don't have to write me the calculation that what you did anymore either, okay? Now, for the dot product, I still want to kind of see, so it's 5 times -6, the sum of the vertical components here, all right? Divided by, now this one, I'm just going to calculate, okay, guys? So it's going to be square root of 29, because it's 5 squared plus 2 squared. This guy is going to be times 36 plus 1, which is 37. All right, so my answer is -32 over root 29 times root 37. All right, and that's my final answer. That's my final ratio for the first step. You haven't answered the question. The question is, what is the angle? So the second step. We're looking for the angle, so we have to do the arc cosine of the quotient. So in your calculator, if you want, you can calculate this first and store it, or you can calculate this first and input that into the answer here. So you should get something like 167.66 degrees. All right, and that makes sense for this angle here because it's definitely up to C, okay? All right. Let's move on to this example. This example I wanted to do because it's the same instructions, but it's written really, it looks more complicated, okay? It looks more complicated than it is. But I want you to utilize, and I think you recognize some of these angles, right? Ooh, ding, 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 okay? Let's write these in component form, by the way, okay? Isn't it just 2 cosine pi over 4 and 2 sine pi over 4, okay? Okay, and then you have V, which is cosine 3 pi over 2 and sine of 3 pi over 2. Okay. Well, this also, the scalar could be removed, right? It could be pulled out because we could apply the same kind of skills, scalar operational properties, right? Okay. And the V will stay. But you guys think about it. Just think about these values here. Okay. Isn't cosine of pi over 4, isn't it like here? Isn't it, are we talking about this angle here? And I think you guys are like, oh, I know this is my angle, right? Isn't this your angle? Okay, and this guy is 3 pi over 2. So let's move 3 pi over 2, which is, I'll use a different marker. Ding, 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 like that, right? So isn't it like actually this right here, this vector, and this vector? But we're trying to find the angle between, right? So we're looking for this angle here, right? So what's that? Our theta is going to be, just use your judgment. It's pi over 4 plus pi over 2, isn't it? Isn't this guy pi over 4? And isn't this guy a right angle, a big fat right angle, okay? Or if you don't like to think that way, it's a angle that makes it 90 degrees, right? Like this, which is a right angle. So that you can think of it this way, which is 3 pi over 4, or you can tell me it's 135 degrees, okay? Yeah, because it's 45 degrees and 90 degrees here, right? So it's angle between is 135, okay? You're right. So when it's obvious like this, it's okay for you to do this with what you know, okay? All right, let's move on to orthogonal vectors. This is the last thing that we're going to cover. And orthogonal vectors sound so fancy, but I'm sorry to say it just means perpendicular. Okay? Hey, orthogonal vectors, perpendicular, not parallel. Okay? Not parallel, right? And what does it take when vectors u and v are orthogonal? They are only orthogonal if and only if u times v, the dot product of u and v, is equal to 0. Easy peasy. So we got to know dot products, right? And orthogonality, okay, has some cool aspects of it when we're doing the work and force problems in physics, okay? Now, number 23, prove vectors u and v are orthogonal. What do they must do? We must prove that this and this, the dot product, is equal to 0. Let's check it out, okay? So let's do that. U times v, it's going to be 2 times 3 over 2 plus 3 times negative 1 because it's u1, u2, v1, v2. And this is u1, v1, u2, v2, okay? And what do I get? I get 3 minus 3, which is 0. Ching ching! Are they orthogonal? And the answer is yes. Definitely orthogonal. Whoa, I know what this means. Uh-oh, okay? All right, so you guys, the last example, but remember, this is example number 23, all right? The next example is like your homework questions too, and I want you to know, how can you tell whether something is orthogonal, parallel, or neither, okay? So let's just see. Let's just first see if they're orthogonal, because you know what that means. Given two vectors, so this guy is a component form, this, component form, -2, -I. You guys, you know, anytime on the video, why don't you guys stop and see if you can do it on your own first, okay? Okay, so I'm going to see, okay? Wait a minute, okay. Okay, so let's just do u times v. So I get 8 times -2 plus 4 times -1. I get -16 minus 4, -20. Definitely not equal to 0. Not orthogonal. Okay, it's not orthogonal. Okay, it's not orthogonal. So is it parallel? Is it neither? Okay, now I want to ask you, what is it like? I wonder what it takes in order for us to show that two vectors are parallel. I mean, if they're not orthogonal, they're not parallel, then obviously it's neither. So we don't need to prove that's neither. But how do you show something is parallel? Then I'm going to leave it like this. You guys, when you see 8, 4 and -2, -1, do you see anything in common here? Okay, I want you to think about something here. Okay, okay. Now, I'll leave it at that, and then we can discuss and see what you come up with. There is something unique about these two vectors, okay? All right, you guys, go